So in this video, we're on etcd.io docs, reading the FAQ, and we're going to go with this first question. What is etcd? It is a consistent distributed key value store, mainly used as a separate coordination service in distributed systems and designed to hold small amounts of data that can fit entirely in memory. So yay for etcd being a small word because it holds small amounts of data in big, aka distributed systems. And look at that, I'm already pronouncing it for you, so we could skip that section. Next question, do clients have to send requests to the etcd leader? So Raft is leader based. The leader handles all client requests which need cluster consensus. However, the client does not need to know which node is the leader. Any request that requires consensus sent to a follower is automatically forwarded to the leader. Requests that do not require consensus, for example serialized reads, can be processed by any cluster member. And when you click Raft, you'll learn a lot more about this consensus algorithm. And at least let's read the abstract together. That should be fun. So this algorithm is for managing a replicated log. It produces a result equivalent to multi-Paxos, and it is as efficient as Paxos, but its structure is different from Paxos. This makes Raft more understandable than Paxos, and also provides a better foundation for building practical systems. Yeah. Who needs practicality, I say? Well, they say they're doing this in order to enhance understandability. Raft separates the key elements of consensus, such as leader election, log replication, and safety. And it enforces a stronger degree of coherency to reduce the number of states that must be considered. Results from a user study demonstrate that Raft is easier for students to learn than Paxos. Raft also includes a new mechanism for changing the cluster membership, which uses overlapping majorities to guarantee safety. Okay, so this is such an interesting paper. I'll go ahead and read it further in a separate video. So what else do we have over here in the etcd FAQ? Well, configuration. What is the difference between listen client URLs or peer URLs? And then advertise-client-URLs or initial-advertise-peer-URLs. So what's the difference between all these words with dashes in them? Well, these two specify the local address etcd server binds to for accepting incoming connections. So when you see listen, think addresses for accepting incoming connections. To listen on a port for all interfaces, specify 0000. The next dash word set we have is advertised client URLs and initial-advertise-peer-urls. These specify the addresses etcd clients or other etcd members should use to contact the etcd server. So here, etcd is like advertising itself. The advertised addresses must be reachable from the remote machines. Do not advertise addresses like localhost or 000 for a production setup, since these addresses are unreachable from remote machines. Now, why doesn't changing the listen URLs update the advertised peer URLs in etcd control member list? Well, a member's advertised peer URLs come from initial advertised peer URLs on initial cluster boot. Changing the listen peer URLs or the initial advertised peers after booting the member won't affect the exported and advertised peer URLs, since changes must go through quorum to avoid membership configuration split brain. Use etcd control member update to update a peer's URLs. These are always fun to read. Deployment system requirements. Since etcd writes data to disk, its performance strongly depends on disk performance. For this reason, SSD is highly recommended. To access whether a disk is fast enough for etcd, one possibility is using a disk benchmarking tool such as FIO. For an example on how to do that, read here. I would give you a quick little look at that, except it's completely blank. To prevent performance degradation or unintentionally overloading the key value store, etcd enforces a configurable storage size quota set to 2 gigabytes by default. To avoid swapping or running out of memory, the machine should have at least as much RAM to cover the quota. 8 gigabytes is suggested for normal environments, that is, and etcd warns at startup if the configured value exceeds it. At CoreOS, an etcd cluster is usually deployed on dedicated CoreOS Container Linux machines with dual-core processors, 2 gigabytes of RAM, and 80 gigabytes of SSD at the very least. Note the performance is intrinsically workload dependent. Please test before production deployment and see hardware for more recommendations. This next question is an interesting one. Why an odd number of cluster members? Like, why does it have to be? Well, an etcd cluster needs a majority of nodes, a quorum, to agree on updates to the cluster state. For a cluster with n members, quorum is n divided by 2 plus 1. For any odd-sized cluster, adding one node will always increase the number of nodes necessary for quorum. Although adding a node to an odd-sized cluster appears better since there are more machines, the fault tolerance is worse since exactly the same number of nodes may fail without losing quorum, but there are more nodes that can fail. If the cluster is in a state where it can't tolerate any more failures, adding a node before removing nodes is dangerous because if the new node fails to register with the cluster, for example, the address is misconfigured, quorum will be permanently lost. What is maximum cluster size? Theoretically, there is no hard limit. However, an etcd cluster probably should have no more than 7 nodes. Google Chubby Lock service, similar to etcd and widely deployed within Google for many years, suggests running 5 nodes. A 5-member etcd cluster can tolerate 2-member failures, which is enough in most cases. Although larger clusters provide better fault tolerance, the write performance suffers because data must be replicated across more machines. What is fault tolerance? An etcd cluster operates so long as a member quorum can be established. If quorum is lost through transient network failures, but then they put in parentheses, for example, partitions, etcd automatically and safely resumes once the network recovers and restores quorum. Raft enforces cluster consistency. For power loss, etcd persists the Raft log to disk. etcd replays the log to the point of failure and resumes cluster participation. For permanent hardware failure, the node may be removed from the cluster through runtime reconfiguration. It is recommended to have an odd number of members in a cluster. An odd-sized cluster tolerates the same number of failures as an even-sized cluster, but with fewer nodes. The difference can be seen by comparing even and odd-sized clusters here. Pause if you want to check their math on that. Adding a member to bring the size of cluster up to an even number doesn't buy additional fault tolerance. Likewise, during a network partition, an odd number of members guarantees that there will always be a majority partition that can continue to operate and be the source of truth when the partition ends. Now, does etcd work in cross-region or cross-data center deployments? Deploying etcd across regions improves etcd's fault tolerance since members are in separate failure domains. The cost is higher consensus requests latency from crossing data center boundaries. Since etcd relies on a member quorum for consensus, the latency from crossing data centers will be somewhat pronounced because at least a majority of cluster members must respond to consensus requests. Additionally, cluster data must be replicated across all peers, so there will be bandwidth cost as well. With longer latencies, the default etcd configuration may cause frequent elections or heartbeat timeouts. See tuning for adjusting timeouts for high latency deployments. That's interesting, election timeouts. I think we can all use one of those. Right, that's it for this video. I'll do a part 2 where I cover more questions and answers from the etcd.io docs.